So whereabouts do you think we're at with quantum theory? I think where we're at right now is we're kind of comfortable with the idea that the theory is, well, it's very mathematical, so it's hard to draw. We're okay with the understanding about orbitals instead of orbits, although we'll probably get those mixed up once in a while. We're probably okay with using quantum theory to describe where the electrons are, what kind of electrons we have, or at least their energies in an atom. What we need to do, though, is to make sure that our theory can also describe or explain bonding. How does bonding happen? With Bohr theory, bonding in covalent terms was fairly easy. You had an overlap of orbits. Does that still work? Well, we're not talking about orbits anymore. We're talking about orbitals. So now what? So what we want to do today is take a look at that and see if we can understand how quantum theory is used to explain bonding. So let's quickly remind ourselves of the quantum numbers and what they mean and how we're going to use them. So we have our numbers n, and n can be any natural number, 1, 2, 3, counting numbers. L is our orbital number, and that starts at 0 and works its way up to as high as n minus 1. Keeping in mind that that's a possibility. It's not that every atom is going to use all those values. And then we have m sub L, and we call that our magnetic number. And m sub L runs from your negative value of L up to your positive value of L. And we'll see how that plays out in a couple of minutes, a little bit more detail. And then we have the spin number, which is just plus 1/2 or minus 1/2. If we were to look at a particular example, and we've done questions like this, of course, in class, if n is equal to 3, you know what to do. You know how to take the L values and come up with those. You know how to come up with the m sub L values, and you know how to come up with the spin values. But here's where we need to pause. In the third energy level, we have room for 18 electrons. And this is something that Bohr understood as well. Bohr had the problem he couldn't predict that and how it filled, but Bohr knew that there were 18 electrons possible in the third energy level. So that means I need to take these quantum numbers and I need to generate 18 possibilities out of that, because every electron has its own set of numbers. All right, so let's look a little bit deeper. Reminding ourselves, of course, that the n is energy level and L is the shape of the orbital. More importantly, not so much what the shape is, but how many different possibilities we have for shapes, or waveforms if you want to use that language. M sub L, and this is where things are going to start to become important, or at least this is where what we do next is going to, M sub L is going to influence what we do next. That's the orientation of the orbital. The more possible values I have for orientation, well, the more possible orbitals I have. And then finally the spin number, well, that's just, I can fit 2 electrons, either spinning plus 1/2 or spinning minus 1/2. I also have to remember that every electron has a unique set of numbers. No 2 electrons have exactly the same 4 numbers. We can have electrons that have the same 3 numbers, but then one would be spinning plus 1/2, the other would be spinning minus 1/2. So I'm going to go back with that n equals 3 example, and I'm going to break it out a little bit. So n equals 3, same as before. Now I'm going to take my values for L and spread them out, because what I want to do is take each L value in turn and look at it independent of the others. What that means is, if L is equal to 0, what does it mean for m sub L? What about when L equals 1? What about when L equals 2? In other words, if L is equal to 2, the m sub L values are -2, -1, 0, 1, 2. And if it's L is equal to 1, then it's -1, 0, 1. In other words, now I have a list of more of the possibilities. You'll notice that some of my numbers get used multiple times. Then if I load up my spin numbers, plus 1/2, minus 1/2, now what I have is a more complete list of the possible combinations. In other words, I can now find all 18 electrons in that list, because each electron will have from one of those numbers. Maybe the n is equal to 3, L is equal to 1, n sub L is equal to -1 and spin is -1/2. Or maybe a different electron has n equals 3, L equals 2, m sub L equals 1, and spin is +1/2. So any one of those combinations I can work with. I'm going to represent each orientation as a box. So each value of m sub L gets its own box. So in the first one orientation, one box. In the second one, 3 possible values, -1, 0, 1, 3 boxes. And the last one, 5 options, 5 boxes. Those are going to represent my orbitals. Now, of course, I have to put electrons into those orbitals. So what do I do with that? I'm not going to use dots. Those work really, really well on Lewis diagrams, but they're not going to work well here. What I'm going to use is I'm going to use an arrow. And fairly arbitrarily, I'm going to use an arrow pointing upwards as a spin +1/2 and an arrow pointing downwards as a spin -1/2. It honestly could be left, right, or some other kind of symbol. It's just an arrow gives us this idea of direction and direction of spin. This is a convention that is used fairly universally. Your textbook doesn't actually use boxes, it uses circles, but I'm using boxes. But arrows, again. So if I have my orbitals like this, so the first one, of course, represents the orbital where L is equal to 0, and there's only one orientation for that. That's spherical. That's the s orbital. And the second set represents the p orbitals where L is equal to 1. Each one of the boxes in that group of 3, the triplets there, those are identical energies, identical kinds of orbitals, identical amount of energy in the orbital, but they're different orientations. If I start to fill electrons into those boxes, I start to draw things like this. Now, we'll pay a little bit more attention in class as to how I know when to pair electrons up, and because I've got 2 pairs and 2 singles, how do I know which one is which, and how do I know how to decide, which is actually kind of redundant, but that's okay. We'll take care of that in class. What I want you to know for now is how I represent an orbital, how I know how many boxes to draw. Do I draw 1 or 3 or 5? And that all comes back to my value of L, which is then m sub L. Phew, it's hard for me too. And then how do I represent bonding? So when I start talking about going from an atom to a molecule now, I have to start forming bonds. So bonds used to be the overlap of orbits. Now they're going to be the overlap of orbitals. So if I take that atom I just drew, I have 2 pairs and 2 singles. Well, it's the single electrons that need to form bonds, and that's almost something going back to grade 10 with your Lewis diagrams that you did at that time. Both those single electrons can pair up, not with each other, but with an electron in another atom. So I can have one electron coming in for one orbital and another one coming in for the other orbital. Now, you may notice that in that example, all the electrons seem to be spinning +1/2. And it really doesn't matter, because when the bond is formed, the electrons pair up and then they will sort out the spin for themselves, we think. It doesn't matter a tremendous amount whether we draw them with both spin up or both spin down, or one up, one down. That's going to be, what we want to do is say this electron and that electron, or this orbital and this orbital, this is where they overlap. So that represents 2 bonds, 2 single bonds. I could, however, also have, in this case, instead of the bonding electrons or the new electrons coming in from 2 separate atoms, they could come in from this one atom on this, 2 electrons on the same atom. And then I could have double overlap or a double bond. And we know about double bonds from Lewis diagrams and from doing Bohr theory as well. Those were also, we could have double bonds there. So quantum theory still works. It still explains what we're observing. It still explains how bonding can happen. We're also going to find that we can use it to explain bonding patterns in things that, remember when we did Lewis diagrams and we ended up with things that, wow, where did that come from? We'll be able to use quantum theory to explain that. However, word of caution is that when we go from an atom to a molecule, things are going to change. And what do I mean by that? Well, short version of the story, It's not that bad. But if electrons in orbitals if the orbital represents just where I'm probably going to find the electron, then once I form bonds and there's more forces involved, where I'm likely to find the electron can actually change. So the atom is no longer static and fixed, it's a little bit more fluid. But that's another lesson for another day and another time. We'll talk to you in class. See you later.